All right, so we've got two integrals right here. This one is known as the sophomore's dream integral, and this one I'm gonna label this guy's little brother, because this one's actually easier to solve, and that makes sense if you think about it, right? We have a natural log here. In an integral, the more complex it is, the higher chance, well, it could help if it's more complex. This one looks a little more intimidating, but they're both pretty cool. So let's go ahead and start with this one as a warm-up for this right here. Okay, so this one, what do we do first? Well, we don't want x as a base, right? We'd rather have e as a base. So I propose we take this x and then make it e to the natural log of x, because it doesn't change anything. So that this negative ln x is still in the power. So here you have e to the, and I'm going to write the natural log of x down, but you still have this guy right here. And then you multiply it by ln x. E to the ln x, that just gives you x. However, there's two natural logs. You just go ahead and rewrite it, right? It's just natural log squared. And we're going to use this notation because it looks cool. Alright, now what does this look similar to? The Gaussian integral, because you have e to the negative something squared, right? And what's the only thing that we need to do right now? Well, it's a substitution. You can't have a natural log there. Let's just substitute natural log. It's going to pump out a nice differential we can take advantage of too, maybe. But yeah, let's make a substitution. Let's call it maybe t. Let t equal to natural log of x. All right, well, let's go ahead and isolate x and then differentiate. So putting an e in the base of both sides, you get e to the t is equal to e to the natural log of x, which is simply x. And then differentiate both sides. Derivative of e to the t is e to the t. Chain rule, multiply by the derivative of t. Right hand side, just multiply by the derivative of x, because yeah, the derivative of x itself is a constant 1 times that, right? Okay, so now what? Well, let's go ahead and sub it in. And don't forget, we also have bounds here. So how are we going to deal with those? Well, these are x bounds. We want them to become t bounds. So the relationship between x and t is exhibited here. The x, you have to take its natural log to get the t value. What's the natural log of 0? Well, if you take a limit, because see here we're integrating on a positive region, if you take a limit from the positive side, then ln of 0 plus is negative infinity. So in terms of t, here we can put down a negative infinity. All right, what about up top? Plugging in infinity here, natural log of infinity, it diverges to infinity. So we now have an integral from negative infinity to infinity. All right, next we have this in here, e to the negative ln whatever. So the e to the negative is going to stay. The natural log of x, notice how we turned it into a t, but it is still squared. Okay, finally we have the dx. dx we saw is equal to e to the t dt. And yeah, that's this step. All right, what's the next step then? Right, because well, here you do have part of the Gaussian integral, but you also have this weird guy hanging off here. How do we deal with this? Integration by parts. You can maybe differentiate this and integrate that, but I don't think that would work, because you're going to end up with a constant on the side, and it ends up messier because you still have an e to the t. You're not getting rid of that. Well, they both have base e. Why don't we just add the powers and see what we get from that? So, in fact, here you can just write down you're integrating over r, because this range right here, just all real numbers, right? All right, I just want to make sure it's still recording. Yeah, you can just call it r though. So you're integrating over the set r. In here, we said we were going to combine the powers, so e to the negative t squared plus t. dt stays there all the same. Okay, now what? Well, whenever you have a quadratic in the argument of a function, usually, usually you would give it completing the square shot, because then stuff can come out of it, right? If you have sum of squares or difference of squares, you can do a trig sub maybe. It just looks nicer if it's not expanded out like this. So let's go ahead and try to complete the square. First step, factor out the negative. You get, well, here. Factor out the negative, you get e to the negative t squared minus t. And how do we complete the square for this? Well, you have to add 1/4 and then subtract 1/4. Right? So this cancels out to 0, and once you distribute in the negative sign, see that it's equal to that. I don't know why I'm explaining that. This is advanced calculus. But not advanced calculus. This is maybe Calc 2. Should be able to figure this out. Anyways, at this point, these three terms is what gives us our binomial square, right? So we still have this 1/4, just take it outside. Negative times negative is positive, so once you bring it outside, it becomes positive 1/4. Like this. Okay. Integrating over r, e to the negative. Okay, so we have these three terms we can just rewrite as binomial squared. And in this case, our binomial is just t minus 1/2 all squared. Then we still have the 1/4 that we were talking about earlier that we can just bring outside. All right, now, does this look much better? It looks kind of complicated still. Notice that this 1/4, even though it looks ugly while tacked on here, right, we can actually just split this guy up. This can become e to the negative, the thing in red, and then times e to the 1/4. So let's bring it up here. Line of continuation, arrow of continuation. Okay, so we're still integrating over r, all real numbers, but we can split off the 1/4 now. So we still have the e to the negative, that thing, t minus 1/2 squared. And now you have a plus 1/4. This just becomes e to the 1/4. In other words, the 4th root of e. Then just write that down on the side, right? There we go. Okay, this in here. Now, this right here, the thing in red, is just a constant. Let's bring it outside in a second. But here, this takes the form of the Gaussian integral because you're integrating over r. And in here, if you just make a quick u substitution, it works out. So let's just make a substitution. Let maybe u equal to t minus 1/2. Differentiate both sides, du, and on the right side, dt. Okay, so yeah. One thing to notice, however, we have bounds, but, and this really means from negative infinity to positive infinity, but plug in negative infinity into t, you still get negative infinity for u. Positive infinity, same deal. So you're still going over r. So we're integrating over r still. Now, earlier we said we we're going to take this constant outside, so let's go ahead and do that. Kind of messy, but we'll write it cleaner later. In here, we still have that thing, except instead of t minus 1/2, well, we set t minus 1/2 equal to u, so it is now u. Don't forget that we still have that square sitting up there, so it is e to the negative u squared. And here, the Papa Gauss pops out, right? Okay, and then we still have the dt, which is just equal to du. Now, I've done a video proving this guy before, and it is equal to the square root of pi, since we're going from negative infinity to positive infinity. I'll link it in one of those card-looking things, but yeah, I'm going to just go ahead and replace that with square root of pi. You can prove this by squaring this whole thing and then converting it to polar coordinates. Okay, so here, the 4th root of e is still sitting outside. But then this thing over here, the integral itself, we can now rewrite as just the square root of pi. And that's it. These are two numbers multiplied together. It looks pretty cool. You can also rewrite this as, well, you can extend the 4th root over everything, e, and then you can just square the pi, right? Because 4th root of pi squared, that's just the square root of pi. Either one of these looks pretty cool. So I'm going to box that, and that's actually our final answer for this one right here. the sophomore's dreams little brother. Okay. Well, now let's go ahead and tackle that one. All right. We're now going to work this out. And it's going to start off a little more complicated, right? Since notice that, well, we're going to do the same thing to the base again, right? Because you don't want x as a base if you have an x in the power. But the issue here is that you're going to have, well, this is already non-elementary. We've been taught this as basic rule in calculus. You can't take the antiderivative of x to the x in any form. But yeah, we're still gonna go ahead and do the thing where we turn it into e and see what we can pull out from that. So, we have the integral from 0 to 1. We want to turn this x into e to the natural log of x. So here, this negative x up top still stays up top, and then this natural log of x just multiplies on. Okay, now this is actually quite different from its little brother, because here we can't do the same thing. If you say u is equal to ln x, you get some weird stacked function, and you don't want that. So instead, well, we have e to the power of something. Why don't we just use a power series, right? We have the Maclaurin series for e, and that uniformly converges as well over its entire domain. So let's go ahead and turn this thing into its power series. Now, as a reminder, e to the, well, what variable should we use? E to the t, very untraditional. You can express this as a power series from n is equal to 0 to infinity of t to the n over n factorial. Now, this right here is a Maclaurin series. You can go ahead and just differentiate this, use a formula for the Maclaurin series to achieve this. I'm not going to go over that right now, but all in all, what I'm trying to do, this right here, it's an exponential function. We're going to turn it into a power series. I'm going to walk through this a little bit slowly, but this should be pretty reasonable. Okay, inside of here, e to the whatever, right? Notice that the whatever is what goes where the t is. So this junk also goes where the t is when we plug it in. So now, let's put it down like this. We have the power series going from, let's use n is equal to 0 to infinity. Now, here, the t just goes straight in, but here we have the negative x ln x. That's still going to go in where we expect it to. So we have negative x ln x to the nth power over n factorial. And then we still have our differential dx. All right, what next? Here what you can try to do is, well, you can't really do much at this point. But however, notice that you can kind of, it's easier to integrate the inside now, at least compared to when it looked like that, right? So what if we just switch the order of these? Now, since this series converges uniformly on its entire, on all real numbers, right? And that means this interval right here, of course, it's included. We can just go ahead and swap these. So this is half rigorous. Let's just do it. So we put the summation first, and then the integral crowbar second. Okay, so we've swapped the order of these. Now what can we do on the inside? Well, let us just distribute the nth power, right? There's a negative 1 multiplied on, right, even though it's represented by a negative sign. So we have negative 1 to the n. All right, well, we have this x, so we have x to the n. And then we have this natural log of x, so that is also to the n. And on bottom, you still have the n factorial, dx. So we split this up into its basic components, right? We have negative 1, we have the x to the n, ln x, and we also have this n factorial sitting on the bottom. It's not all grouped up like that now. So let's go ahead and integrate this with respect to x. However, we have this other junk bothering us. We have this negative 1 to the n and this n factorial. Now notice that they don't have any x inside of them, right? N isn't in terms of x, n is independent. So we can just go ahead and move it outside of this integral. Yeah, because the integral is linear. So let's go ahead and do that. We have this series, capital sigma going from n is equal to 0 to infinity. Okay. And then, yeah, let's go ahead and just move that out. So out here now we have our -1 to the n over n factorial. And we can't move, this factorial is ugly. And you can't move this x to the n or ln x to the n outside because it has an x inside of it. So we gotta just integrate it. So let's go ahead and put down the integral sign. X to the n, now natural log of x all to the nth power. Okay, what's the next step after this? Well, we have a polynomial times a logarithm, and that's not preferable. However, well, let's just make a substitution, right? If we set u equal to the logarithm, then this x becomes an exponential, e to the u. And it's much better to have an exponential times a polynomial than a polynomial times this natural log looking thing. So let's make a substitution. Right. So we can do let's use u equal to, well, negative natural log of x. And the reason why we're using this negative is actually going to become more apparent in just a second. But if you were to just do normal natural log of x, then the apparent properties that would have popped out in a second won't. So let's just stick with the natural log of x for now. The negative version for now, and I'll go ahead and explain what's going on in just a second. All right. So now let's isolate x, because we have this x right here. We need to figure out what that is. If you go ahead and negate both sides, this becomes negative u is equal to your natural log. Then put a base of e on both sides. You get e to the negative u is equal to x. All right, pretty simple. And then one more thing, we have to find our dx. So let's just differentiate both sides. Differentiating left-hand side, you get negative e to the negative u. And then, you also need to do chain rule. So in here, the derivative of u is du. And on the right-hand side, the derivative of x is 1. Yeah, and then chain rule, multiply on the dx. All right, we're limited for room down here, so I'm going to take it up there. Okay, so we just copy it down again. We have our infinite summation from n is equal to 0 to infinity. And then we have our alternating guy, and then it's over n factorial, right? So that's so far. If it was just this by itself, we didn't have the integral, this would just evaluate to 1 over e, right? But unfortunately, we still have this to deal with. All right, well, next let's put down our crowbar and let's figure out the bounds. These are in terms of x. You can plug them in to get them in terms of u. So yeah, let's go ahead and figure out these bounds in terms of u. This right here, this is a 0 for the lower bound. Now, natural log of 0 is undefined, but just like earlier, since we're integrating over a positive region, if you took a limit, this would be 0 plus, since you're approaching from the positive side. ln of 0 plus, well, it approaches negative infinity, so this would be negative infinity. But we still have this negative sign, so it becomes positive infinity. So the lower bound becomes positive infinity. And that's, you can kind of think of that as the reason why we use this negative, so that we would have a positive infinity, right? It's better to, there's a lot more variation, there's a lot more manipulations that we can make with a positive infinity than a negative infinity. And there's a lot more properties that take advantage of this positive infinity instead. Okay, what's next? For upper bound is easier. Just go ahead and plug it in. Natural log of 1 is 0. So negative 0 is still 0. So the top bound is just 0. Okay. Next, let's deal with this natural log of x guy first. Now we saw that, well, we know this is true, right? But this isn't a negative natural log of x. This is a positive natural log of x. So how do we sort that out? Well, see this right here? Let's drag it inside. So I'm going to do some small scratch work on the side. So we're going to have this sum still going on. But and we can write down the 1 over n factorial. But the point I'm trying to get at here is, well, integral whatever, dot dot dot, right? Because this polynomial doesn't really matter to us. We're trying to figure out how the hell we pull out a negative natural log of x. So this right here, this and that, you can multiply them together, right? You would get, well, negative 1 to the n times natural log of x to the n. And because of this property of exponents, you can just kind of factor it out inside the exponent, if that makes any sense whatsoever. So inside, you still have the negative ln x, and then after you move the factor it, the n out, it becomes this. So in actuality, if you just ignore this, well, you can turn it into your negative natural log of x, which is u. What that means for here is that, well, we're going to take advantage of this trick, right? So here, let's just go ahead and get rid of this, since we're going to go ahead and pull it inside to give us some help. All right, so let's go ahead and do that now. Right here, rather right here, we have negative natural log of x to the nth. Negative natural log of x, we said, is u, so this is really u to the n. Okay, next step, we have this polynomial. This polynomial doesn't change by the fact that we pull it inside, so we can just work from it from here. We saw that x is just equal to e to the negative u, and we still have to raise it to the nth power. So the powers are going to multiply. N times negative u, you get e to the negative nu. All right. Finally, we have our differential dx, which is just that thing. So I'm gonna negative e to the negative u du. So I'm just gonna write that down. Nearly run out of room. Okay. So we have this now. What do we want to do? I'm gonna get rid of the scratch work now. Well, notice that these bounds kind of odd, and we have a negative here that we can use to reverse them. So let's just go ahead and get rid of this negative and flip it. Pretty simple to wrap your mind around. So we have all this prerequisite stuff, and then we use this negative sign from the differential, and then flip the bounds. Okay, well, what are we left with? Inside, you have u to the n. That doesn't change. However, notice that you have base e twice. Now, you can go ahead and ignore that negative since we already used it. So all we really have is negative n u, and then e to the negative u. If you go ahead and add the exponents, here's what you get. You get negative nu stays, and then you still have this negative u up top. So you just do minus u. All right. Okay, now what? Well, here we can do more work, right? We can go ahead and factor out a negative u and see what happens. So we still have this right here. You have u to the n, and then factor out the u. Okay, in the first term, you move the negative outside, you move the u outside, you're just left with the n. And then the second term, you moved everything outside, so you're just left with the 1. All right, this is about as simple as it gets, right? What can we do here that will help us out a little? Well, take a look at the structure, right? We have u to the n, and we have e to the negative u times something. Let's try to maybe, because, all right, here's my train of thought. We have the proper bounds, right? 0 to infinity. We have the polynomial part, and we have the exponential part. All together, this almost looks like the gamma function, right? If you just write it out, the gamma function of n, in this case, is we have the bounds, right? And then I'm going to use t to the n minus 1, e to the negative t dt. So you can see that we're actually almost there. We have this polynomial part. We almost have this exponential part. All we need to do is just get rid of that n plus 1. Simple, because do it using another substitution. Let's use maybe s. Why not? So let s equal to that guy, right? Sorry, not including the negative, since here we still have the negative left, right? We want a negative variable, so we can't include the negative because then that would become a positive e to the s and fuck stuff up. So anyways, s should be equal to u times n plus 1. Differentiate both sides. Well, actually, you know what? Here we have a u that, well, what can we do with that, right? Well, we need to isolate it in our substitution to be able to figure out what the hell that's going to be after we make it. Just divide both sides by n plus 1. So s over n plus 1 equals u. All right, now we need to find our differential du. Differentiate both sides. So on the left-hand side, our s is our variable, so, and our over n plus 1, that's really just a constant that's multiplied on. So the constant stays. And then the derivative of s is just ds. Okay, right-hand side, the derivative of u is just du. Not that bad. All right, let's go ahead and plug it in, and we can go through this a little slowlier this time. All right, so let's write down our power series infinity boy. 1 over n factorial. Okay, crowbar. Once again, we have to evaluate bounds. Now, notice that these are in terms of, well, sorry, no, ignore the gamma right here. We're working with the black function because this is where we got our math from. Notice this is in terms of u, and we want it in terms of s. So plug it in here. 0 times anything is going to be 0. So bottom bound, pretty easy. It's going to be 0. Now, infinity, on the other hand, right? Infinity times something positive gives you another infinity. But infinity times, if this were to be negative, that would give you negative infinity. So that screws us up a little bit. However, notice that here, can it be negative? N runs from 0 to infinity. Plug in 0, which is the least it can get, and you just get a positive 1. So, and since it's never going to dip below 0, you're never going to have a negative number right here. So because this is always positive, infinity, right, we got that from here, times something positive is always just going to be positive infinity, right? So the top bound is just s is equal to positive infinity. All right, so same bounds. Now what next? This right here, u to the n. What's u? S to the s over n minus 1. So you can go ahead and write it like this. Sorry, not n minus 1, n plus 1. Now, we're still raising the whole thing to the nth power, right? But I'm going to go ahead and distribute the nth power both onto the numerator and onto the denominator. So it's going to look something like this. All right. Right here, e to the, whatever the fuck that is. The e's and the bottom's going to stay, right? That's just a number. All right. But, and the negative's still going to be there. However, we set u times n plus 1 right here to be s. So all we need to put down there is an s. Okay, now finally our differential ds over n plus 1 is just du. So we go ahead and put this into where that once was. All right. So we have our new integral that we're going to work with. Well, what can we do now? Notice that here we have an n plus 1, and it's multiplied by an n plus 1, but to the nth power, right? Now you can kind of treat this as n plus 1 to the first power. And because they're multiplying, you can, and they have the same base, right? The base is n plus 1, and because they're multiplying, you can just go ahead and add the powers. So let's write this down again. Integral from 0 to infinity. This s to the n, well, you know what? Let's write down the n plus 1 stuff first. So this is in the denominator. N plus 1, the base is the same, right? So we can keep that there. But then since the base is the same and they're multiplying, you can add the powers. Interesting, right? All right, and then we have our s to the n and then e to the negative s. And then ds. All right, now first notice here that we don't have any s's inside of this factor right here, so we can go ahead and move that outside. So really just think of only this black part being inside of this integral. This is almost the gamma function, right? Just replace this t here with an s, and we've got an n instead of n minus 1. But this n instead of n minus 1 is actually useful to us. And why is that? Well, let's move this back up. Yeah, I'm going to get rid of this first column right here. Okay, well, why is that useful? It's because I'm going to write some more properties of the gamma function out. So here, what do we have in terms of gamma? We have s to the n, not n minus 1. So if you added 1 to, well, okay, here. If you plugged in gamma of n plus 1, sorry, I'm going to write this higher because I'm going to need the boom. If you plugged in gamma of n plus 1, what does that get you? Well, we still have the integral bar. That doesn't change. The only thing that changes is where the input actually comes in, right there. We have t to the, that thing, t to the n, right? The input, really. So our input here is n plus 1, but we still have this minus 1, so they actually just cancel. No need to write it. And then we have e to the negative t dt. So notice that what we have going on here, s to the n, e to the negative s, is really just gamma of n plus 1, t to the n, e to the negative t. Okay, so why is that important? Well, this gamma of n plus 1 is actually just n factorial. And you can go ahead and plug in some numbers for n. All you really need to do is integration by parts. Say you plug in 2, right? You would get just 2 out of this. Say you plugged in 6, you would get, what's 6 factorial? 720 out of this. This right here is just n factorial. Okay, so, well, let's go over what this means. First, I want to, instead of skipping too far ahead, I just want to go ahead and move this bitch boy outside. So we have the infinite summation from n is equal to 0 going to infinity of 1 over n factorial. And yeah, we're going to pull an n factorial out of here. It's going to cancel with this, and it's going to look pretty cool. But I want to move this guy outside. So 1 over n plus 1 to the n plus 1. Okay. Then we can put down our crowbar, integral from 0 to infinity, and then we have s to the n, e to the negative s, whatever, ds. Okay. Now, what did I say? This right here is really just n factorial, and I explained why earlier, and I'm actually going to derive the gamma function. If I ever do that, I'm going to put one of those card things again. I'm not going to point at it, because I think that looks stupid. But yeah, I'm going to derive where this actually came from. Like, how the hell did you get this out of a factorial? But anyways, all you got to know is that this right here is really just n factorial. So let's put that down. N is equal to 0 to infinity, 1 over n factorial, and then 1 over n plus 1 to the n plus 1, and then this whole integral thing, as I said, just becomes n factorial. Now, something cool happens. This and that, they're going to cancel. And you're back almost with something that looks really nice. Now notice that all of the n's that are still left here are n plus 1. So in reality, what this is just 1 over 1 to the 1 after you plug in 0, right? Plus 1 over 2 to the 2, plus 1 over 3 to the 3. So we can really just start at 1, right? And then have just n to the n instead of n plus 1. And this right here, although it may not seem any more simplified, well, first of all, you're actually able to approximate this using this, right? Just plug in the numbers. You get 1 over 1 plus 1, 1 over 1 to the 1, plus 1 over 2 to the 2, plus 1 over 3 to the 3, etc. And that gives you a really good approximation for what this value actually is. But the other cool thing about this is, well, give me 1 second. You can rewrite this inside of here as just n to the negative n. So I'm going to write it up here like this. All right. In summary, we have this whole thing being equal to the infinity void from n is equal to 1 to infinity of 1 over n to the n, which we can rewrite as n to the negative n. Now, why is that cool? Because in the argument of both of these, you have x to the negative x, n to the negative n. However, here you have an integral, and here you have a sum, and the cool thing is the integral is going from 0 to 1, and the sum is going from 1 to positive infinity. They have the same exact form, and there's actually a way you can generalize this integral right here, but this is why it's called the Sophomore's dream, because just look at that, it's a nice relationship. And this actually evaluates to, I'm not sure, you can go ahead and try to approximate. I'm pretty sure it's like 1.2 something, or maybe that's 0 to infinity. If you had this be from on the positive real numbers, this would actually converge, right? To like, yeah, it would converge to something. This right here converges really fast though, right? Because n to the n grows really quickly. When you have it in the denominator, it approaches infinity hella fast. Meaning your numbers eventually, as you keep adding, they approach 0 really quickly as well. But yeah, that is the result for the Sophomore's dream integral.